Hello, I'm Dr. James Dborin, co-founder of DoubleWord AI, and we're back with another Behind the Stack video where we're going to be talking about model parallelism. In this video, we're going to talk about three things. We're going to talk about what is model parallelism and why would you use it. We're going to give an introduction to two forms of parallelism, the two most common forms that you see in inference workloads, tensor and pipeline parallelism. And then we're going to talk about their relative merits and talk about which one you choose in which situation. So starting with what do we mean by model parallelism? Model parallelism is when we have a model that's potentially too large to fit on a single GPU. And so we choose to run it across multiple GPUs and hope to do so in a smart way to optimize whatever metrics it is at inference time that we care about, be that throughput or latency or anything else. So if I have a very large model, for example, like the large MOE models like the Qwen 235 billion parameter model, it's very unlikely that this will ever fit on a single GPU, or at least not in the near future. And so you often need multiple GPUs in order to run it. If you have small GPUs like L4s or A10s, which have only 24 gigabytes of VRAM, even moderately sized models need multiple GPUs to run it. So model parallelism is something you run into all the time, as well as the fact that it's a more efficient way of utilizing multiple GPUs, even if your model fits onto a single GPU, because you don't have to duplicate the weights over the GPUs. So we care about parallelism in the cases where we have multiple GPUs, we want to use them together to run a large model, or we have a small model and we want to maximally utilize our GPUs by not wasting the VRAM on duplicated weights. And the two most common types of parallelism that you see, and they're available in essentially all inference engines, are tensor and pipeline model parallelism. They have very different characteristics, these two model parallelism methods. And so in this video, we're going to introduce what they mean and then talk about their relative merits to make it a bit easier to know which one to choose when you're deploying your own language model. So let's start with tensor parallelism. And to start, we're going to introduce some notation. What I have on the screen is like a schematic of a matrix multiplication, which is one of the sort of largest and most important building blocks of language model, of like a language model architecture. Essentially, everything a language model does is matrix multiplication in some form. And so we're going to look closely at this, but first we need to become a bit familiar with this notation. What we have here is, on the left, we have the input matrix. In a transformer, this will be like your activations. So the temporary tensors that get created during a model's inference. And then up here we have the model's weights, one of the many billions of parameters of weights that the model has. And the way that you should look at this is, if you're familiar with matrix multiplication, you take a row and then you do a dot product with a column from the other matrix and you store that result here. And that's how you view this. So the value here is a product of this vector and that vector being multiplied together. And when I say dot product, I mean you walk through these one at a time and you multiply each value together and then add up all the resulting values and you store it here. So this is like a schematic of a matrix multiplication that lets you reason about the sort of shapes and things on each and the shapes of the matrices and as they're stored on each GPU. So this is what it looks like when you store. This is like a matrix multiplication happening on a single GPU. But what if we have a matrix that's too large to even store in my VRAM? Maybe it's a very large matrix, maybe I have a very small GPU, but I still want to be able to calculate the matrix multiplication of these two matrices. So how can I do that? Well, you can do something like this. You can split the various matrices up and store them on different GPUs. So in the grayed out bit is the part of the matrix that I'm not storing on my GPU, and the bit in color is the bit that I am storing. So on GPU 0, we have these matrices in red, and on GPU 1, we have these matrices in blue. And on each matrix, on each GPU, I calculate this output matrix of the same shape. And in order to get the true value of the matrix, of the output matrix here, the true value of the matrix multiplication, I add these together. So I sum them together across the two GPUs. And there's good primitives, libraries like the Nickel library for NVIDIA GPUs for doing this sort of thing, for saying take the outputs on each GPU and sum them together. And so if we look at what we've done here, let's look particularly at the weights. So in the weights, I've managed to compute the full matrix multiplication, the full forward pass of this model, storing only half of the weights on each GPU. And since pretty much all the weights are matrix multiplications in a language model, if you did this form of parallelism across two GPUs, you should be able to store a model that's twice as big than you could on a single GPU. And you get more benefits from this than just being able to store the model. So during your inference, if this matrix is very big, you often can spend a long fraction of your inference time waiting for one of two things. If you're bandwidth bound, which happens during decoding when the model is producing tokens, then you're waiting for these weights to get loaded into the compute units of your GPU. And if you're compute bound during prefill, when these activations are large, when you have many tokens sort of along this dimension, then you spend most of your time waiting for it's actually doing the maths. So you end up sort of compute bound or flop bound once the weights are loaded. So in this setup, in the tensor parallel setup, in both cases we benefit, because when we're bandwidth bound, each GPU is only pulling in half of the weights, so it happens twice as quickly. So in principle, for the same workload, the same sort of decoding batch size, you should be able to achieve up to 2 times faster inference by splitting the same model over 2 GPUs to doubling the bandwidth. In practice, you're not completely bandwidth bound, like that's not the only thing you're waiting for, but in theory, you should be able to get up to the pipeline parallel degree speed up during decoding, and the same is true during prefilling. Across your 2 GPUs, you have twice as many flops available, so you should be able to inference the same amount of prefill tokens in half the time if you're like completely compute bound. Obviously, that doesn't quite happen in practice, but that's like a nice theoretical benefit. So the picture I've drawn here isn't quite how you do tensor parallelism in practice. The problem with this is that after every single matrix multiplication, you have to do this communication step where you sum the two up. And in practice, you can actually do a bit better by utilizing the structure of like how we do matrix multiplications in transformers. So here is a slightly more realistic picture of how you would do matrix multiplications in a transformer. So zooming in on one GPU, what you have is your input activations, and then you have 2 matrix multiplications, one after another. And what you do is that on the temporary activation that you create here, you apply some sort of nonlinearity. Often this is an element-wise multiplication via another matrix multiplication. So we actually have 3 matrix multiplications, but it doesn't change much with analysis. It might be like a ReLU activation. In attention, it's a softmax activation. But this sort of pattern of having 3 matrices and doing 2 back-to-back matrix multiplications with a nonlinearity in between is the vast majority of work that transformers do. And so we'll analyze like how you can do a bit better than the above parallelism scheme. So what we do is we take each pair of matrix multiplications and we split them along different dimensions. The first one we split along the column like this, and the second one we split along the row like this. So what happens is here we get half of the activations that we would have otherwise. The GPU 0 gets the first half of the columns, GPU 1 gets the second half. Then in the second matrix multiplication, we create the correct sized output, and then only after this do we sum them together. So this is nice because this communication step is non-trivial, it does take some time, and it's fully exposed, you can't hide it particularly well. So the benefit of this scheme is that you do half as much communicating as in the previous scheme. In the previous scheme that I showed you above, you would communicate after this step to recover the full matrix, and then you would communicate again after this step. So you actually get a 2x communication saving. This is a similar thing that you do for flash attention. Like when you shard flash attention over multiple GPUs, you do this and you put different heads for the multi-headed attention. You put different heads on each GPU, but the sort of shape of it looks quite similar to this. So that's a rough outline of how you do tensor parallelism. So let's move on to pipeline parallelism before we talk about their relative merits. So in pipeline parallelism, I'm going to outline this with a 3 GPU setup that I might have. And on each GPU, I'm storing a subset of the layers of the model. Let's say my model has 60 layers. Then on GPU 0, I'll store layers 0 to 20. On GPU 1, I'll store layers 20 to 40. And on GPU 2, I'll store layers 40 to 60. So you could do this without any real power. So if I just did this and I sent a request into this setup, you can actually inference it really simply without any sort of parallelism. So we're going to indicate a request with a square box. So at some time equals 1, I have my blob of requests. This might be 128 requests or something. I send it to GPU 0. I run through layers 0 to 20. Then I send it to GPU 1 at time equals 2. And I run it through layers 20 to 40. And then I send it to GPU 2 at time equals 3. And I run it through layers 40 to 60, and then I get my answer, my 128 tokens. This is great. I mean, now you've managed to inference your model, and it's bigger than any one of your GPUs. It's 3 times bigger than you could fit on one GPU. But you're really not making great use of your expensive GPU resources. In all of these time slots, your GPU is idle, and in fact, the vast majority of the time it's idle. Only 1/3 of these time slots are you using your GPUs. So, and that gets worse and worse the higher degree pipeline parallelism you have. If you have a node of 8 GPUs and you do a pipeline like this, you end up with sort of 1/8 of your GPU time being used. So it's very expensive and a very poor utilization way to use your GPUs. But we can do a bit better than this, and this isn't actually pipelining anything, right? There's no form of parallelism. This is just serial inference. It's kind of the same as an offloading scheme, where you store your these layers in CPU RAM or on disk, and then while this is inferencing the first 20 layers, you sort of swap these in. It's not too dissimilar to an offloading scheme, which would at least give you higher utilization in this. But we can make better utilization of our GPUs by actually pipelining this and having GPUs inference in parallel. So the way we can do this is by increasing the effective global batch size. So each GPU is still only processing 128 tokens at a time. But while GPU 1 is processing its 128 tokens, we can start GPU 0 processing the next set of 128 tokens. In this case, I have sort of 3 times 128 tokens in my global batch, and I've split them into mini batches or micro batches of 128 tokens each. And then when GPU 0 is done processing its set of 128 sends it to GPU 1, and then GPU 0 can begin processing the next set of 128. And so in this case, I have all of my GPUs working maximally all the time. I'm not so obviously wasting GPUs. They're not sitting idle. They're processing all of these requests in parallel. So now I'm able to service 3 times 128 people instead of 1 times 128 people. And you're making efficient use of your GPUs. What you'll notice is there's still some like GPU wastage here. We have this bit at the start, and you'll have the same at the end, where no GPUs are being used. And this is called a pipeline bubble. But if you're operating under sufficiently high load, it's kind of fine, because if you sort of extend this out and you have constant batches of 128 coming through your system, overall it's going to be that this pipeline is very small and your GPUs are sort of maximally utilized, and the pipeline will only happen at the start, at the end, or like during down periods. So it's fine to have like a small bubble. Certainly better than what we had before. Now, unlike tensor parallelism, you'll notice that this doesn't really improve the latency. Each request still follows the exact same path that it took before. This still has like the latency of like running on a single GPU. It doesn't feel like one request is accelerated by having triple the flops or triple the bandwidth in this case, but your overall throughput of your system improves because you're able to use those spare flops and bandwidth to process the next set of requests. So this really is like a throughput-oriented pipeline parallelism setup. So now that we've got an idea of what the two different types of parallelism look like, let's discuss their relative merits. So the benefits of tensor parallelism are that especially during decoding, if you're bandwidth bound, this can give significantly better throughput than pipeline parallelism. So this is important to note. This is only true for bandwidth bound, for bandwidth bound operations. I'll see if I can give a brief idea why. So if I have like a tensor parallel setup and I'm running with 32, or if I have one GPU setup, so tensor parallel is 1, and I'm running with a single batch of 32, which maxes out my memory, and this achieves a throughput of T, so some throughput value T. And then I go to a tensor parallel 2 setup. Now I'll be able to run with a batch of 64. I've doubled my memory, but I'm running with a batch of 64, but the time that it takes to produce these tokens, this set of 64 tokens, is actually half of what it was before. The reason it's half is that during decoding, the thing that bottlenecks us is moving the weights from the VRAM into the compute units of the GPU. And just because I'm running with twice as many requests, that doesn't change. The time it takes to bring the weights in is the same, or the amount of memory you need to bring in is the same. But because I'm using 2 GPUs, I effectively have double the bandwidth. So now, I'm producing 64 tokens instead of 32, and I'm doing it in half the time. Therefore, my output is 40, not T. So it's 4 times greater than the single GPU setup. And this is only true if you're like very strongly bandwidth bound, but there are sort of realistic scenarios where you can see this. And if we do the same analysis for pipeline parallelism here, so I have two GPUs. I send one set of requests of 32 there, and it's in the next here. Each of these requests takes half the time to process because you're only processing half the layers. But you have to do two of them. You have to do twice as many of these requests. So this is the same time step as processing 32 tokens on one GPU, but you're producing 64, so the total throughput is 2T. So you can see that if I have two GPUs and I'm very strongly bandwidth bound, which might happen during like a reasoning model, like producing lots of tokens, or like a very small model producing lots of tokens, if I do tensor parallelism, I can achieve 2 times the decoding throughput of pipeline parallelism. This is like a theoretical 2 times throughput. You're not guaranteed to achieve this. There's lots of asterisks in this calculation, but in general, you would expect that going from one GPU to two GPUs like this, tensor parallel throughput in these like low compute settings scales better than pipeline parallelism throughput. So if you can use tensor parallelism, it's worth trying it first and benchmarking both, but you should expect to see that under some circumstances, tensor parallelism has a higher overall throughput than the same for pipeline parallelism. Now, if you're doing like very prefill heavy workloads, very long input context lengths, these two become closer together. They sort of approach the same throughput. So it's worth noting that for certain workloads, this isn't the case. So this makes it look like tensor parallelism is sort of strictly better. The downside of tensor parallelism is the communication, the comms overhead. So in tensor parallelism, after your matrix multiplications, you have to have this communication step where you sum together the different matrices. You can't hide this latency. There are sort of tricks where you can hide it, but you fundamentally, like, you have to wait for this communication step to happen. And so in general, tensor parallelism is better the faster the communication, especially if you're interested in low latency applications. You need faster communications to make tensor parallelism work. The nice thing about pipeline parallelism is that while you're doing this communication step, you can be using the various GPUs. This one can be running the next set, and this one can be running the previous set, whichever was sort of happening before it. And so you can hide a lot of that communication. And presumably with pipeline parallelism, you're not doing it for a latency improvement anyway, so you're not so concerned about this. So often the recommendation with tensor parallelism is that you can do it within a node. So a node of GPUs is like a set of GPUs connected either with PCIe or connected with something like NVLink, which gives them fast communications. If I have two nodes, each with 8 GPUs like this, these GPUs are connected together with very fast interconnects, and so it makes sense to do tensor parallelism across these two, like within these nodes. But across these nodes, you tend to have a very slow interconnect, or like relatively slow. And if that's the case, it's kind of tricky to do tensor parallelism across them because that latency isn't going to be hidden. There are tricks around this. People use something like InfiniBand or some other fast interconnect to connect these nodes together, and then you can do very high degree tensor parallelism, but it tends to require slightly more tricks, slightly more like clever optimizations to be able to get good throughput and good latency in these setups. So if you have a model that can't even fit on a single node, like the 600 billion parameter DeepSeek model, there's many sort of such 8 GPU nodes that can't fit this. One strategy to overcome this memory bottleneck is to have pipeline parallelism connecting these two nodes. So on one node, you have the first half of the model. On the other node, you have the second half. And then you're not sending as much data down this interconnect. And you're getting the benefits of tensor parallelism within each fast node. So this, and while you're communicating the activations across this barrier, your first node can start processing the next batch of data. And this is quite a common setup for extremely large models on nodes that can't fit them. So to wrap up, today we've looked at two different types of parallelism, tensor parallelism and pipeline parallelism. And we've talked about their relative merits and when you should choose them for your inference workloads. And then talked a bit about what you do as you get to very large model sizes and have to mix them across nodes. Thank you for listening, and we